We're going to continue with kinematics, where we started, or where we left off, I should say, last time. This kinematics 2. We're going to start with a problem. Okay. So car accelerates from 28 meters per second to 10 meters per second. And actually, you know, often people would say decelerates. That's fine. I don't care. It's slowing down, right? In a span of 4 seconds. A. Calculate the acceleration of the vehicle. B. Find its displacement change. This is its displacement during deceleration. And C. Draw a detailed. By detailed, I just mean with numbers on it. It doesn't have to be like super high end, but just with numbers on it. Draw a detailed position time, velocity time, acceleration time graph of the motion. Okay, so it has to have numbers on it. One thing you won't know is where on the displacement time graph. So we could just say this starts at 0 meters. So wherever the acceleration starts, make that 0 meters on your position time graph. Okay? So we'll pause and let you have a crack at this. Okay, so step 1. Let's calculate acceleration. So acceleration is change in velocity for a change in time. Now before we get too far, actually, I want to visualize what's going on in this situation using graphs. Okay, so we'll do a velocity time, a position time, and an acceleration time graph here. All right, so let's think about this. A car deaccelerates or decelerates from 28 meters per second to 10 meters per second in a span of 4 seconds. So let's velocity time that first. Okay, so it starts at 28, and then sometime later it's at 10, and that's meters per second, and that takes 4 seconds for that to happen. Okay, so you're going to get this. All right, so what's that going to look like in terms of a position time graphs? This is where you have to like use your noodle. Think about it. Okay, so this object is traveling to the right, but it is slowing down. So it slows from 28 to 10. Okay, it doesn't go completely flat, because completely flat here would indicate a velocity of 0. So we have now a negative acceleration. So put that in. So we have this, and acceleration and time. Okay, so let's just remember, right? The instantaneous velocities here are shown by tangent lines. Okay, so there's my slope at the beginning. There's my velocity and slope a little bit later and a little bit later. And by the very end, right, this slope is dropped to 10 meters per second. So let's actually just write those in to make sure we're understanding this fully. So by the end, the slope of my position time graph has dropped to 10 meters per second. That's represented here on this graph. And my initial was 28 meters per second. Okay. So from going from here to here, we use the slope. Okay. V equals delta D over delta T. Then, going from here to here, we also use this slope. So now, acceleration is delta V, change in V over delta T. So we get this. The slope on this graph never changes because we have a constant acceleration the whole time. Now we got to figure out what that acceleration is. So that acceleration is just going to be the slope of this graph here. So let's just show how we do that. Okay, so rise over run. So rise here, our rise, run here. So delta y over delta x. So final minus initial, so 28 minus 10 over a delta of 4 seconds. Yeah, actually, sorry, I just realized something here, or it was pointed out to me. It's got to be final minus initial. We have to end up with a negative value here. So it should be 10 minus 28. Okay, so that should be negative 18 divided by 4. Well, divided by 2 is 9, so it should be negative 4.5 meters per second squared. Okay, and that is what we graph out over here, a constant negative 4.5 meters per second squared. Perfect. Phase 1 done. All right, so now we've got the acceleration figured out. How much distance was covered while this happened? So last time we learned a little method for dealing with that, which said, well, what you do is you take the average velocity and you find the area underneath here, okay? And what we're essentially saying is that the area here under this block has the same area as this like triangular, shape here, this like half house shape, all right? So this is what we're going with. So if we find this area, we should be able to find the distance that we covered, right? And the reason this is okay to do is because as we talked about last time, the area under a velocity time graph gives us delta D. Okay, so it equals velocity times time. But now we have to deal with the average velocity. Okay, average velocity here because we have a changing velocity, so we have to use the average to find this value. So then delta D is VF plus VI over 2, right? That gives us halfway in between 28 and 10 times T. Okay, so 10 plus 28 divided by 2 times 4 seconds. Okay. And we should put units in here. I'm kind of forgetting to put units in. So meters per second times seconds, we get 76 meters. Seconds cancel off. Perfect. So the area under here then, 76 meters. And on my graph, I end up 76 meters after I started counting. Okay, assuming that the starting point of this is at 0. Okay. All right, and there we go. And just to illustrate a final point here, if we had to work backwards from here to here to here, we could have done that, right? Because we say that the delta v, the change in velocity, well, actually we couldn't. We actually couldn't have, and I'll tell you why in a second. So the delta v is going to be equal to negative 4.5. So actually, sorry here. Delta v is equal to acceleration times time, right? So I'm taking this formula and rearranging. So let's just see what that gives us. So negative 4.5 meters per second squared for 4 seconds, 918 equals negative 18 meters per second. So take note here. This gives us the change in velocity. If we actually want to know what our final velocity is, we have to have our initial, right? So to look at that, that's this. VF minus VI equals negative 18 meters per second. If we put in a value for the initial, say, at 10, now we can go ahead and figure out where we were at to start. Okay?